These notes will cover everything you need to know about the strength of the kinetic friction force for AP Physics C. First, remember what kinetic friction is. Kinetic makes it sound like moving, but actually it's more specific than that. It's one solid surface sliding on top of another. So not something flying through the air and hitting air molecules, and not a rolling wheel that's not sliding, something that's rolling without skidding. No, that's not kinetic friction. It has to be sliding. The cause of this friction is something we discussed in ninth grade. If you imagine a book on a table, it looks like one smooth surface on another. But if you could look microscopically, you'd see that both are rough. That's our model for it. We don't need to know about atoms. We just know that both surfaces are actually rough. They're not smooth. So if you think of this and kind of reason it out, this force of kinetic friction should depend on a couple of things that we could control. It depends on what two surfaces you use, because some are very smooth and some are much rougher, like sandpaper would be rougher than just a book by itself. So it should depend on the types of surfaces. And then the other thing, think of what you could do with those two surfaces to increase how much those teeth mesh together. What could you do with these two? If they're just like this, you don't get much friction, but if they get pushed into each other, then you get a lot. So the second thing that could alter the strength of the force of friction will be how hard these two are pushed together. So we'll put force. Force, pushing, M. So the force pushing them together. Well, we've already learned about that force. We have a name for it. What force is that a book applies this way to a table, or that one flat surface or that the table applies this way to a book as a flat surface, or that the book applies this way to the table as also a flat surface? Well, that's the normal force. When I first learned this in high school, I would get confused about these sort of things, and I would think, well, which one is it? Which one do I plug in the equation? The force that the table pushes up, the force that the book pushes down on the table, which one is it? Which one's more important? I'm confused. Do I plug them both in? And the answer is you're plugging in the strength of a force. And by Newton's third law, it's the same strength in both directions. If the table pushes upward on the book with a normal force of, say, 12 newtons, then the book pushes downward on the table with the same strength of a normal force. So what you're going to do is take the number for that strength. You're not really thinking of which one it is. They both have the same strength, and that's a number, and you're taking that number. That's what's important, as a single number. And that's what you'll say, well, what if I push harder this way than this? That's not possible. Newton's third law says if the table pushes this way on the book with 12 newtons, the book must push this way on the table with 12 newtons. All right, let me do a demonstration of this to go through these different factors here, these different variables. And what I have here is a book and a force meter. And it's a little crowded here, but I think you'll be able to see what's going on with the force meter. Now remember, the book has to be sliding. We're not asking how much force it takes to start the book moving. That's not what we're interested in. We're interested in the force it takes to keep it moving. So let me do this here. So the book, kind of our control, the book by itself, like that, on a smooth surface, I get about 4 or 5 newtons. If I want to change the normal force, I could put a brick on the book. Now I get 8 newtons. Okay, I've not changed the weight of the book. I've not changed the gravity force on the book. I've put a brick on it, and that's increased the force between the book and the box. And to show you that, to drive home that point, instead of putting a brick on it, I'm going to push down. So normally, we'll say our control is about 5 or 6 newtons. And if I push down on the book, I can make that a whole 10 newtons to keep it going. Right, so I've got 10 newtons. There we go, 10 newtons to keep the book going. In no way have I changed the weight force on this book. Gravity's not pulling down on it more because I'm doing this. What I've increased is the force between the book and, we'll call this the table, and the table. I've increased the normal force because now it's got to counteract the gravity force on the book and the push I'm doing to keep the book stationary in this direction. All right, so that shows you if we change the normal force, we get different numbers for the friction force. What if we change the surface? So I had between 3 and 5 newtons of force to pull it when it was a smooth book on the table. I've got sandpaper on the other side, so let's do that and see what we get if we change it. Now, haven't changed the normal force, still the same normal force as our control, but now we have a different surface, sandpaper on cardboard box. Okay, now we have between 8 and 9 newtons. Instead of, say, 5, we now get 8 or 9 to keep it going. All right, so we've changed these two surfaces that were in contact. All right, to come up with a formula for this, it doesn't follow from any particular theory. We derive this formula by doing experiments. We develop the formula by doing experiments. So now I'm going to put up the results of a kind of imaginary experiment where the numbers are too perfect. They're too perfect, they're made up so that you can quickly see the pattern. Okay, we do this in 9th grade, so I'll go fairly quickly. Imagine instead of a book across a cardboard box, I drag a tire across white concrete, and I keep changing the normal force, and I measure the friction force. And I do the same thing with gold on gold, and I measure the kinetic friction force for that situation. First thing you'll notice is I've got the same normal forces in each, but I get very different friction forces. So that shows you it depends on the combination of surfaces. The second thing is as the normal force increases, so does the friction force, as we would expect. The third thing is to look at these numbers and ask yourself, what's the relationship like? Now, just like x, y, we put our independent variable here and our dependent variable there. We think of the normal force as something that we are controlling, and the friction force as something that results. That's just a point of view, a human point of view. So think of it that way, and think of how you would write this as a function of that. Just as when you do x, y, you write y as a function of x. The one that goes in this column is your dependent variable. You want to write that by itself on one side, generally the left side, and then you write everything else on the right side. So what would go over here, and it should have Fn in it, and obviously the answer is 0.5 times Fn. Now you might have thought of putting Fn over 2 or 1/2, but when these sort of things are done and we have a coefficient in front of a variable, in science, especially a coefficient that's different, right? They could be different here and different there. Scientists and engineers like to write it as a decimal. It's easier to quickly compare decimals. You wouldn't want to compare, say, 32/67 to 41/95 or something like that, right? So we write them as decimals because we can compare them quickly. All right, let's do the same thing over here, and you should be pausing the video and figuring this out on your own before I do it to make sure you understand it. Okay, look at this case, very different, 2.5 Fn. And I picked these two examples for a reason. I want to show you that this coefficient here can be smaller than 1 or it can be larger than 1. Most of the time it will be 1 or smaller, and that can lead a beginner to assume it's one of those coefficients that can never be larger than 1. It isn't. There's some coefficients in electromagnetism that are like that. They can never be larger than 1 or they can never be smaller than 1. It's nothing like that. It can be smaller than 1, it can be equal to 1, it can be more than 1. But generally it's in the vicinity of, say, 0.01 to 3. It's rare to find anything with a coefficient of friction like with 11. I don't think I've ever seen something that big in a table. So from looking at that, from those two examples, you can come up with a general formula that will turn out to work well for lots of different experiments, for lots of different combinations of surfaces. The force of kinetic friction, just as in our previous one, was some number, which was 0.5 for one of them and 2.5 for the other, times the normal force. A nice linear relationship between these two quantities. And we find that's generally true for surfaces that we have slide over, one over the other. The force of kinetic friction equals some number that's different for different surfaces times the normal force. This number here is a coefficient, of course, coefficient of a variable. It's called a coefficient of kinetic friction. That's a pretty obvious name. But of course, no one wants to write out coefficient of kinetic friction here, so scientists picked a symbol for it. They picked this symbol, which I suspect it's mu. That symbol is mu from 9th grade. That's a Greek lowercase m. Americans tend to pronounce it mu. There are some countries that pronounce it mu. Either is fine. I suspect the reason they picked mu is if you think of the general equation of a line, and when we study friction for different surfaces, the y-intercept is 0, the b is 0, you have that, but they didn't want to use the letter m, it stands for mass in formulas, so they picked the Greek lowercase m. To drive home that point, it's kind of like the equation of a line going through the origin. All right, so that's the symbol. Now look at this and see if you can figure out what the unit for mu would be. This is in newtons and that's in newtons. Okay? The unit is, it has no unit. Because this is in newtons and that's in newtons. So you don't need this to be in any unit to cancel anything out and give you newtons. Sorry, in newtons. Or imagine solving for this. You would move this under here and you get newtons over newtons, which goes away. It's a pure number. Mu is a pure number, a pure coefficient number. So that has a consequence, and that consequence is, since it's a pure number, that means the two forces can be in any units. They don't have, this is not, when you get that the mu is 0.5 or 2.5, that's fixed and absolute. And it doesn't matter whether your forces are in pounds or newtons or if there's any other unit for force. As long as they're in the same unit. You can't have newtons and pounds. But they could both be in pounds or they could both be in newtons. And the mu would stay the same. Unlike the capital G for gravity, if we used the gravity formula and plugged in feet in the bottom instead of meters, you'd have to use a different value for G to get the correct answer. So let's write the equation up here for the force of kinetic friction. This is like the dependent variable. This is the dependent variable. This is the independent variable. And this, what would that be? What would that tell you mathematically? Well, in a lab, I don't know if we'll do this in AP Physics C. We will probably not do the friction lab because you did it in 9th grade. But you could be asked to analyze such a lab on the AP test or on my test. And if I gave you a set of data, I would give you worse data than what you did. I wouldn't give you perfect data. You would have to plot it. And you should get something that looks like that as your plot. If you plot kinetic friction versus normal force, and it should fall on a line. This equation predicts that your data would fall on a line, and the slope of that line would be the coefficient of kinetic friction, the mu. So this graph summarizes all that. Now I want you to notice something about this equation. It's really important when you're doing physics, not just to keep track of what you know or what's involved, keep track of what's there, but keep track of what's not there. Keep track, know in your mind what's not a factor, what the kinetic friction does not depend on, what is irrelevant and has no effect on it, because a problem could have many different variables in the problem, and you have to be able to pick out the ones that actually affect kinetic friction and ignore the ones that don't. So look at this. You look up these in a table. You can Google such a table, and the regular physics book has such a table. Your book doesn't for some reason. So you can Google a table of those. Those are fixed numbers, so obviously they don't depend on the surface area of the tire or book or whatever, and there's no place here for the speed. So if you have a problem where they give you the surface area of something moving sideways and you're asked to calculate kinetic friction, you ignore this. Likewise, it doesn't matter how fast it's going. As soon as the kinetic friction is kind of the friendly friction compared to the force of air resistance or the force of static friction, which are more complicated. As soon as the object is in motion, as soon as that book is sliding, you can instantly calculate the force of kinetic friction if you know these things. You don't have to worry about how fast it's sliding. You don't have to worry about whether it's slowing down or speeding up. You don't have to worry about whether it's in an angle as long as you can get the normal force. All you need to know is the mu for the two surfaces and the normal force, and you got it. It doesn't depend on how big the object is, and it doesn't depend on its speed. It only depends on those two things. Okay, so we'll finish with a point I like to make, which is probably not on any AP test, but if you go into science or engineering, you should know this distinction. When you begin, you often confuse an axiom, a postulate, a definition, a law, a theorem, and now we're adding the word model. So I want to make clear why this is considered a model, not a law. In real life, the force of kinetic friction may depend a little bit on the area, and I know it definitely depends on the speed. You get different amounts of kinetic friction depending on whether the tire is skidding slowly or quickly. Further, if you looked at this accurately, you would see it's generally not perfectly straight. there will generally be another term where fn is squared and possibly even a term where fn is cubed. Those are called higher order terms. What we've got is a simpler version of what actually would be a much more complicated formula. This is a model. It's a very good approximation to what really happens, but it's not absolutely true to our measurement's degree of accuracy in every case that we measure, the way a law is, like Newton's law of universal gravitation was before 1900. As far as anyone could tell, it was pretty much always true for anything we measured. That's why that is called a law. But this, however, we know right off the bat, it's not the whole story. So when something is a simpler version of a better equation, and we know it's not the whole story, we call it a model. Now, if you want to get philosophical, in reality, all your formulas are models. All your formulas, laws and models are both models. The law of universal gravitation can be called a model. But in common everyday scientific conversation, we distinguish between these two. Basically, always true for everything we ever do in a class or in a lab or in our field of study. Here, model means a simpler version of something we actually know is more complicated. Since this is linear and it's raised only to the first power or first order, this is what you call a first order approximation. So you hear that term if you go into some sciences, statistics, math, engineering especially, where you have to make approximations. This would be called the first order approximation. And someone might say, well, that's not good enough, we're getting bad results. Let's use the second order approximation, then we use another term with, say, fn squared.